Okay, hello students. In the previous session, we have discussed about the structure of the graph and the properties of the graph, different definitions related with the graph structure. In this particular unit, we have also discussed about the graph representation tactics like adjacency matrix and adjacency list. So in this particular session, we are going to discuss about the graph traversal techniques. So as we already discussed, the traversal can be categorized into two categories. One is the depth first traversal and another one is the breadth first traversal. So what is the depth first traversal? So if each vertex in a graph, before we go for this depth first traversal, let's have a briefer idea about traversal techniques. So as we already discussed, to visit each and every node in a tree, in case of tree, we have called it as a traversal. Similar thing is there in graph also. If each vertex in a graph is to be traversed by tree based algorithms such as DFS or BFS, then the algorithm must be called at least once for each connected component of the graph. This is easily accomplished by iterating through all the vertices of the graph, performing the algorithm on each vertex that is still unvisited when examined. So whenever we are going to traverse a graph, we have to traverse each and every component of the graph, and the component should be connected component of that graph. So to accomplish this, we have to iterate through all the vertices of the graph by performing the algorithm on each vertex that is still unvisited when examined. And as we have already stated that when we visit certain vertices of a particular graph, we may find the adjacent nodes connected to it, and then we are going to repeat this algorithm for the next vertex. We have to make sure that should be repeated on the vertices which were previously unvisited. Visited vertices we are going to avoid. Okay, so in short, we are going to traverse each and every connected component of the graph at least once. So depth first traversal or depth first search for a graph is similar to the depth first traversal of the tree. The only difference here is, unlike trees, graphs may contain cycles. So we may come to the same node again and again. To avoid processing a node more than once, we use an extra array, that is a Boolean array, which marks the visited nodes that you have traversed. So we use a Boolean visited array. A depth first search is an algorithm for traversing finite graph. DFS visits the child vertices before visiting the sibling vertices. So this is very important point. When we are visiting the graph with help of DFS, we should visit the child vertices before we visit its sibling vertices. In short, we are going to the depth first, and then we are going to come backtrack. That is, it traverses the depth of any particular path before exploring its breadth. So obviously in this case, a stack is generally used when implementing this kind of algorithm. And obviously this stack is nothing but the program call stack via recursion. That means in this case, the memory itself acts as a stack, because you are recursively calling the same function for performing depth first search. The algorithm begins with a chosen root vertex. Obviously the root is not the term in a graph, but as we have stated that we are going to traverse the same fashion as the DFS we have performed on a tree, and we know that when we traverse a tree, we start with a root node. So assume in this case any random node in a graph as a root node, and we will start our algorithm with this chosen root vertex. It then iteratively transitions from the current vertex to an adjacent but unvisited vertex until it can no longer find an unexplored vertex to transition to from its current location. So you have to traverse till you visit the unexplored vertex. If unexplored vertices are over, that means whichever adjacent node you have identified, if all adjacent nodes are marked visited, in that case you need to stop and come back to the current location. The algorithm then backtracks along previously visited vertices until it finds a vertex, until it finds a vertex connected to yet more uncharted territory. It will then proceed down to the new path as it had before, backtracking as it encounters dead ends and ending only when the algorithm has backtracked past the original root vertex from the very first step. Obviously that will be part of your stack, and as we know that stack is a LIFO data structure, that will be the first element that you have inserted into the stack. So whenever you are removing the vertices from the stack, while backtracking, root is the vertex which will be visited at the end. So this is how your DFS is going to work. Okay. So let's have a brief discussion with respect to this theoretical concept. We are going to write an algorithm for depth first traversal or depth first search of a graph. So if you see, initially there is no vertex is visited. So initially I will set all the elements of the visited array as a 0. As we have stated, we are going to use a Boolean array. So 0 and 1 is going to mark whether the the vertex is visited or not. So initially, as we haven't visited any vertex, we need to mark this visited array, that means all vertex in that visited array, to 0. So as and when I visit the vertex, I will mark that particular vertex as a 1. So how many vertex will be there? How many vertex we need to traverse? Obviously the n vertex we have to traverse. All vertex, as we have already stated in the definition of the DFS, all vertex must be visited at least once. So this loop will iterate for I is equal to 0 to I less than n for n vertices, and for all vertices the value is currently set for the visited array is equal to 0. Once we are completed with this, we will accept a starting vertex v from the user. As we already stated, we have to decide any random vertex that will be the root of your DFS. So we will accept that particular vertex v, and then I will pass that vertex v to the DFS routine or algorithm. If you see here, this is my actual routine where I will perform the depth first search. Here I have passed, or we have received the past vertex v. So as we already know the depth first search, how it is going to work: first the root, then the left, and then the right. Are you getting this one? In case of a tree. So in this case, it is not the concept of left and right, it will be the concept of the adjacent nodes. So whichever node you have visited first, that I will print. That means whenever I am printing a vertex, it indicates that I have visited that particular vertex. Now as and when I print that vertex, immediately I will set the value of vertex visited array for the vertex is equal to 1. So visited of v will be set to 1. Now here onward, I will start addressing the vertex w or w's, multiple vertex might be present, those are adjacent to v. And if that adjacent vertex is not part of the visited array, then I will perform this particular DFS routine. Now in this case, I am recursively calling the DFS routine, but now in this case, instead of vertex v, the adjacent vertex w is passed, which fulfill this particular condition, which is not part of the visited array. Unvisited vertex is going to be passed. So this is how your depth first algorithm is going to be there. Now let's see one example for our understanding, so that we can clearly understand this particular algorithm. So here we can see one graph, which is a connected graph. As we know, all the vertices are connected with each other, all components are connected, and as per our definition, we can visit all connected components, all vertices, and then we can perform the depth first search for that. Okay, so for that purpose, first of all, I will take one array, one data structure, Boolean array we have discussed, that is visited array, where I can enlist all the nodes or all the vertices present in that particular graph, and initially I will set this values, as we already stated, to 0 as per our algorithm, and as and when I add that particular vertex to the depth first search or the traversal routine, I will mark that particular vertex as the visited one. Okay. Here your memory is acting as a stack, so as per recursive call, this particular vertices are going to be inserted in this particular stack. So here we have to perform this particular depth first search starting with row D. So in this case, the vertex given by user V is equal to D. So this vertex V is eventually going to be passed to the routine DFS. Okay, and there I am going to perform the depth first search. Okay. Let's see. As we know that this is the vertex, the first statement is to print that D. So we have printed that D, and immediately we have marked that particular vertex D in visited array as a 1. It indicates that that particular vertex is visited. Then we are going to check how many vertices are there which are the adjacent vertices of node D, and we are going to visit the adjacent vertices which are not marked visited in visited array. Before we do that, first of all, that means that the recursive goal is going to call, I will push that data D onto the stack top. Okay. So in this case, when we are we have vertices, adjacent vertices for D are C, F and E, and the order we are going to follow for the traversal is the alphabetical order. So whichever will come first in the alphabet list, that will be visited first. So in this case, the sequence should be somewhat like this: C, E and F. So for vertex D, C, E and F, these are the adjacent vertices, and as per the alphabetical order, this is the way I should visit the particular vertex. Okay. So in this case, I will insert the C in a visited array as a 1, because we know that it is not marked as a 1, that means it is unvisited array, so that will be pushed onto the stack. Now when we visit C, the adjacent vertices for C are, there is no vertex which is adjacent to C. Okay. Therefore I will backtrack to the position where I have visited, that is D. There I can, how I can backtrack is by removing the element from the stack top, that we already know. Okay. So here C is going to be removed, and we are going to restore its previous state to D. Now when we come back to D again, if you see, the adjacent vertices for D were C, E and F, out of which C is already marked as visited in visited array, so C is not our choice as per alphabetical order. The next vertices as per alphabetical order of choice will be E. We know that E is not marked in visited array, so E can be traversed. So now in this case, E is going to be traversed, and so now in this case, E is going to be traversed, the E is going to be printed, and it will be pushed onto the stack by marking it in a visited array as a 1. Okay. So right now we have visited 3 nodes, right now at vertex E. So I need to find the adjacent vertex for the E, which is nothing but G. For adjacent vertex for E will be G. As we know that G is not marked yet, so I can visit this node G in a DFS fashion. Therefore it should be printed over here Okay, it will be printed, it will be pushed onto the stack, it will be marked as a 1, that means as a visited. Now next case, if you see, the next adjacent vertex for G is H and D. So for alphabetical order, that should be D and H. But if you see carefully, D is already visited over here, therefore D is marked as a 1 in this case. Okay, and therefore obvious choice we will have will be vertex H. We know that vertex H is not yet marked, so I can traverse vertex H in DFS fashion, and therefore the next node I should visit should be H. So H is added as a part of the stack top. Here I have marked it as a visited, and here I have marked it as a visited 1. Okay, so this is the order of depth first search till H. Once this part is done, I need to find the adjacent vertex for the H. So if you see, the adjacent vertex for H will be A and B, and as per the alphabetical order also it should be A and B. So here I will have these two vertices which are adjacent to H, out of which alphabetical order A is going to be visited first. Are you getting this one? So in this case, A is going to be visited, that will be added as a part of the stack top, that will be marked as a 1, and that will be get printed over here. Once this part is done, the adjacent vertex for A will be obviously B, and we know that B is not visited yet, so in DFS fashion I can visit B. Are you getting this one? Therefore that will be added as a part of the stack top, it will be marked as a 1, and it will get printed over here. Okay, now when I see the adjacent node for B, I don't find any adjacent node, so in that case I need to backtrack and visit back to the previous state. Are you getting this one? So B is going to be popped, the previous state was the A. So when I come to A, I come to know that there are no more adjacent node except B, which is already visited, and therefore A is also going to be popped out of the stack. Then I visit back node H. Here I come to know that the adjacent node for H is B, which is already visited, and therefore H is also going to be popped out of the stack. When I come to vertex G, here I come to know that the adjacent vertices for G are H and D, D and H, where D is also visited and H is also visited, therefore G is also going to be popped out of the stack. Then I visit back to the node, that means the previous state is node E, where the adjacent node vertex for E is G, which is already visited, and therefore E is also going to be popped out of the stack. Now once you come back, you come to know that the previous state of the vertex is reached to the first node from where we have started. D is the node. Now for D, we have already seen that the adjacent vertices are C, E and F. As we know that C is already visited, E is also already visited, so only vertex which is not visited, or the adjacent vertex which is not visited of the D, is vertex F. So obviously the F is going to be visited in DFS fashion, so F is going to be pushed onto the stack top. Okay, so it will be pushed onto the stack top, F is going to be marked as a 1, and F will get printed over here. And if you see over here, we have visited nearly each and every node, not nearly, all nodes we have, or all vertices we have visited. And if you see the visited area also, it is completely marked by 1. Are you getting this one? So there is no other node left for the traversing purpose. So here, for again, with respect to algorithm, we'll check for F, the adjacent node is C, which is already visited, therefore F is going to be popped out of the stack. Again, At the end we'll come to know that the visited array is D, and it means that we have reached the root node of the particular graph. So I will check visited array, there are no unvisited node, and therefore D is going to be popped out. Are you getting this one? So this will be the answer, where you can see that the stack is empty at the end and our DFS part is done. Three conditions we are going to check: stack is empty, visited array is completely marked, and each and every node of the, or each and every vertex of that particular graph is successfully visited. Okay, so same DFS algorithm we can implement in non-recursive fashion also. Obviously in this case we have to explicitly use the stack operations, push and pop, which we haven't used in case of the recursive routine, where the memory itself acts as a stack, and automatically the vertices are going to be pushed onto the stack, and when we are backtracking, those are going to be popped out of the stack after the condition ends. Okay? So here if you see, first of all, same routine I am going to follow. I will mark each and every vertex of the visited array as 0 initially. I will push vertex V, which I have accepted from the user, okay? And I will mark the vertex in visited array, that is visited of V is equal to 1. Then I will perform the iterative routine, as we already stated that I will remove the element from the stack top. First of all, I will print it, and for each vertex W, which is adjacent to vertex V, I am going to check this particular condition, whether it is a part of the visited array or not. If it is not, then I am going to push it onto the stack, and I will set the visited array for that particular adjacent vertex as the 1. Okay, so this part will repeatedly execute again and again, and eventually it will stop when either you reach the dead end, or either you reach the end of the routine. Okay, so this is about depth first search or depth first traversal of the graph. It's somewhat similar to your tree only, but in this case instead of left and right, we are moving with respect to the adjacent nodes. And I will go to the deeper part unless and until there is no other option for it. Okay, once I reach the, or once I hit the dead end, I will backtrack, and then I will visit the remaining nodes. Okay, so this is the graph that we will see for the depth first search. Okay, so this particular graph you need to traverse with the help of depth first traversal, and your starting vertex is 0. So you start with vertex 0, and you will visit each and every vertex of this particular graph in DFS fashion. Okay, so if we want to see this particular routine in more precise way, so I have created a separate animation for this, or separate steps for this, which will let you know clearly how this is actually happening. Are you getting this one? So we are going to construct a depth first search spanning tree for the given graph. This is also called as a spanning tree. What is spanning tree? That we will see again in the upcoming lecture. So let's see how we are going to concentrate on these vertices. So these are the vertices of the graph. We have adjacency matrix for this, so I can come to know that which nodes are adjacent to that particular vertex. We have an unvisited array, we have a stack for this. So here I will start with vertex 0, as we have already stated over here. I will start with vertex 0, and then I will mark this particular vertex 0 as 1 in the visited array that we have done. Then I will push this vertex 0 onto the stack, and then I will visit unvisited adjacent vertices of the vertex 0 in DFS fashion. So how you will come to know that which are the adjacent vertices of the 0? Either by looking at the graph also you can come to know that, or otherwise by finding the adjacency matrix also. So if you see the adjacency matrix for 0, this row is indicating that vertex 1 and vertex 2 are the adjacent vertex of the vertex 0. Okay. So in short, I have shown those adjacent vertices just close to the node that I am visiting. And here is the legend, that means color coding I have used. If the node is marked with a red color, it indicates that it is the visited node in a graph. If this particular array is marked as a green, it means that that node is already visited, that adjacent node is already visited. If it is a blue, it indicates that it is the next node to be visited, and if it is a gray, it indicates that the adjacent node which is not yet visited. So in this case, if you see, 0 is already traversed, and the adjacent nodes for the 0 are 1 and 2, out of which as per the order, numeric order in this case, these nodes are not alphabets, these nodes are numerals, and therefore I am going to follow the numeric order from 1 to 9, 0 to 9 in other words. Okay, so 0 is already visited. Now in this case, the next adjacent node that I should visit as per the numeric order should be 1, therefore I have marked this as a blue. 2 is also an adjacent node, but it is not yet visited, unvisited, therefore that cell is marked as a gray colored. Okay. So this particular next node is going to be considered over here, and therefore if you see, I have marked that particular node as the red color. So start with the vertex 1. Now in this case, mark this vertex 1 as a 1 in a visited array, push the vertex 1 onto the stack top, okay, and then again repeatedly call this particular DFS function, where you are going to visit the unvisited adjacent node or adjacent vertices for the vertex 1. Are you getting this one? And therefore the next step should be like this. The next vertex I am going to visit will be 3, because this is undirected graph, and therefore the adjacent vertices for vertex 1 will be 0, 3 and 4. As per the numeric order, we go with a 0, but we know that 0 is already visited. If you see, 0 is marked as a green colored cell. The next vertex which is not visited was the 3, and therefore I will mark it as a blue. That indicates that that is the next adjacent node that we need to visit. Okay. So in this case, 3 is going to be visited. So arrow is showing you the direction also, how we are moving forward in this particular depth first search. And if you see carefully, we are trying to visit the depth first unless and until we hit the dead end. Okay. So in this case, 3 is going to be visited. So I will mark 3 as a 1 in a visited array. I will push that 3 onto the stack top. Then I will visit unvisited adjacent vertices of vertex 3 in DFS fashion. So if you see, adjacent vertices for 3 will be 1 and 7. Okay. So when I visit those nodes, I can find that 1 is already visited. The next adjacent vertex I should visit should be 7. So parallelly, if you see, I am printing the DFS order also here. Okay. So here the next adjacent vertexes that need to be visited should be 7. So I will mark 7 with red color. I will mark it in a visited array as 1. I will push that vertex onto the stack top. Then I will go for the visited unvisited node, unvisited adjacent node of the vertex 7. So in this case, adjacent nodes for the vertex 7 are 3, 4, 5, 6, out of which 3 is already visited and 4, 5, 6 is not visited. So as per the numeric order, 4 is the next node that I should visit. Are you getting this one? So start with the vertex 4, mark the vertex 4 in a visited array as a 1, then push it onto the stack top, and then again repeat this procedure of the depth first search for the adjacent unvisited vertices of vertex 4. So if you see, adjacent vertices for 4 are 1 and 7, and if you see, both 1 and 7 are marked with a green color. So it indicates that we have hit the dead end. Hereafter I cannot move forward, so I need to backtrack, and therefore I will, if you see in the previous slide, the stack top was a 4, and once I visit the dead end, the element which we are going to delete will be the topmost element on the stack top. So 4 is going to be what we can say popped out of the stack, and we have performed the backtrack. So after 4, the next node that I should visit should be 7. So once I backtrack to 7, we will come to know that 3 and 4 both are already marked as a green, because 3 is also visited, 4 is also visited, which is adjacent of 7. So the next in a line will be 5. Okay, so the next node we are going to visit will be 5. So here I will visit the node 5, I will mark it as a blue, I will push it onto the stack, I will mark its value as a 1 in a visited array, then I will try to repeat the DFS again for this particular vertex, adjacent vertices of the vertex 5. So if you see here, the adjacent vertices for the 5 are 2 and 7, out of which, if you see carefully, as per alphabetical order, as per numeric order, obviously 2 is going to be visited, but at the same time in a figure you will come to know that 7 is also marked as a green, which is already visited. Okay, so the next vertex I am going to visit will be 2. Okay, so here 2 is going to be printed, and then I will push it onto the stack, I will mark it as a 1, and I will visit the unvisited adjacent vertices of the node 2. So if you see, node 2 have 2 adjacent vertices, node 2 has 2 adjacent vertices, in this case 3 adjacent vertices. In this case it will be 0, 5 and 6. As per the numeric order, 0 is visited, 5 is also visited, so the next node that I should visit will be 6. So if you see parallelly on this side also, this adjacent vertices I have written, I have changed their color. Every time I visit it, I will mark it with a green color. Okay. So the next node is going to be visited will be 6. So therefore 6 is going to be marked as a red. It will be marked as a 1 in a visited array. The element is pushed onto the stack top. Now when I visit 6, I will come to know that the adjacent vertices for the 6 are 2 and 7, where 2 is also already visited, 7 is also already visited. So I will backtrack to the vertex, and therefore I will remove the element from the stack top. So stack is removed from the stack top. The next element that I should visit will be 2. Okay, then I will go to the 2 also. I will come to know that each and every vertex of adjacent vertex of the vertex 2, that is 0, 5, 6 are already visited and marked again. Therefore I will perform the backtrack operation. I will remove it from the stack top. So 2 is removed from the stack top. Then I will visit the node 5. Okay, so here also I will come to know that the adjacent vertices for 5 are 2 and 7, and which are already visited. Perform the backtrack operation, remove the element from the stack top. So the next element I should visit should be, or the vertex should be 7. So when I come to 7, I will come to know that adjacent vertices for 7, that is 3, 4, 5 and 6 are already marked or already traversed, and therefore I should perform the backtrack operation here also. So I will remove the 7 from the stack top. So the next element to be visited should be 3rd. So 3 at 3 will come to know that the adjacent vertices are 1 and 7, which are also already visited and marked green, and therefore I should perform the backtrack operation. So I will remove the element 3 from the stack top. So the next node or the vertex should be visited will be 1. Again when I come to vertex 1, the adjacent vertices for the 1 are 0, 3, 4. Again I will see the visited array, all are marked or are marked green, and therefore it indicates that I should perform the backtrack operation. So I will remove the element from the stack top. So 1 is removed from the stack. So the next node I should visit will be 0. So when I come to 0, I will come to know that the adjacent vertex for 0, 1 and 2 are also visited. So I need to perform again backtrack operation and remove the element from the stack top. But now in this case, if you see, we have reached the root node. So that is when I perform the backtrack and pop the element from the stack top, my stack will become empty. And if you see, the all elements of the visited array are marked. Stack is empty, all the elements are already visited, and this is the final DFS order for the nodes that we have to visit. So if I remove the unnecessary edges, if you see in the previous graph, these are the some unnecessary edges. If I remove that unnecessary edges, you will get this DFS spanning tree. Are you getting this one? So if you see these vertices I have visited, the total number of vertices in this particular graph are 8, and as per the definition of the spanning tree, the vertices in a spanning tree should be n-1, that is 7. Total number of nodes are 8, therefore total 7 vertices should be there. Okay, so this is your DFS or depth first search spanning tree after you perform the DFS operation. So this I think will be little helpful for you to understand the concept of the depth first search. Okay, so I guess today we'll stop for the depth first traversal of this particular graph. In the next session we will discuss about the implementation part of the breadth first search. Okay.